Hello everyone, I'm Venkatesh Srinivasan and I'm here to talk about partial evaluation of machine code. For those of you who are unfamiliar with partial evaluation, here's a 1-minute primer. Partial evaluation is a framework for specializing and optimizing programs. The idea is, given a program that takes multiple inputs and given values for some of the inputs, the partial evaluator produces a residual program that is specialized or optimized with respect to the input values provided. For example, here we have a par program that computes x plus y par n, and if we give the values y is equal to 1 and n is equal to 2, the partial evaluator produces a residual program that is optimized to compute x plus 1 squared. Partial evaluation is a uniform way of achieving optimization such as constant propagation and folding, loop unrolling, function inlining, etc. However, note that these optimizations are not explicitly built into a partial evaluator per se. We have created a partial evaluator called Viper, which is an acronym for the Wisconsin Partial Evaluator. Viper takes in machine code programs or binaries as inputs and produces specialized binaries as outputs. Viper is a partial evaluator for Intel's IA32 ISA. However, it is straightforward to adapt Viper to work on other ISAs as well. So first of all, why do we need partial evaluation of machine code? Well, suppose you have a binary that lacks source code and or documentation. This binary could be an old legacy binary, or it could be a bloated piece of software downloaded from somewhere. Now suppose that there is a set of very frequently used inputs to this binary, and we would like to create an optimized version of this binary that we can execute specifically for those inputs. However, existing binary rewriting tools cannot specialize a binary with respect to common inputs. Now consider another use case. Suppose you want to extract an executable component from a binary. This component can be used in embedded environments where executable size matters, or it can be linked against other programs that require the component. However, existing binary rewriting tools also cannot extract a component from a binary. So all we can do is execute our slow bloated binary and let it make our lives miserable. If we have a machine code partial evaluator, we can address both the use cases that I just talked about. We can specialize a par binary with respect to the value 2 for the exponent to obtain an optimized square binary. We can also specialize the gzip binary with respect to the -d flag to extract a component that only decompresses. Okay, machine code partial evaluation seems to be useful, but why do I need to create a new partial evaluator? There are so many existing partial evaluators that work on source code and other intermediate representations. Why can't I just use them for machine code? Well, you can't. There are certain issues that arise uniquely in the context of machine code partial evaluation, and existing partial evaluators are not really equipped to handle those issues. I'll describe why this is the case in upcoming slides. Now, before I present Viper's algorithm, let me briefly describe the design of a source code partial evaluator for an imperative language such as C. What I'm about to describe to you in the upcoming slides is a summary of the work done by Neil Jones and the Danish School of Partial Evaluation. Most partial evaluators are offline, that is, they work in two phases, binding time analysis or BTA, followed by specialization. BTA is an analysis that determines a priori which parts of the program can be evaluated in specialized a way and which parts need to be residuated. The inputs to BTA are the program and a division or classification of the inputs to the program as static or dynamic. Values for static inputs are known at specialization time, and those of dynamic inputs are unknown. In this example, because we know the values of y and n, y is equal to 1 and n is equal to 2, we classify them static and x is classified dynamic. The output of BTA is a division of all the expressions and statements in the program as static or dynamic. A key property that BTA has to ensure is congruence, that is, anything that depends on a dynamic variable or expression must be classified dynamic. BTA is usually implemented either by using data flow analysis or forward slicing to determine the parts of the program that depend on dynamic inputs. These parts are classified dynamic, and the remaining parts are classified static. Sometimes static expressions can occur in dynamic contexts, and in such cases, the specializer must residuate code for these expressions. The partial evaluator lifts such expressions. Lifted acts as an interface between the two binding times, static and dynamic. So the next phase is specialization, and the inputs to a specializer are the program, the BTA annotations, and a partial static store that maps static inputs to values. And the output is the residual program. BTA ensures congruence, and congruence ensures that static expressions and statements can be completely evaluated. So the specializer uses a primitive called eval for evaluation. It uses a primitive called reduce to residuate code for dynamic statements with lifted expressions. Reduce is usually implemented by simply substituting values for variables in the abstract syntax trees of expressions and statements. Finally, if a statement is completely dynamic, then the specializer just emits it. Now let's use these three primitives to specialize the power program. So the first statement is dynamic, so we just emit it. The next statement is static, so we evaluate it, obtain the post store. The next statement is dynamic with a lifted expression, so we invoke reduce to get the residual expression. Then we go around the loop once more, and we invoke reduce again. Then we evaluate the loop header, but this time we exit the body of the loop, and the final statement is dynamic, so we just emit it. And thus, we obtain the residual program. Now, we are ready to look at Viper's algorithm. At a high level, Viper is similar to the source code partial evaluator we just looked at. Viper is offline. It works in two phases, BTA followed by specialization. However, Viper has novel aspects in its design specifically to address the issues arising in machine code partial evaluation, which the source code partial evaluator cannot normally handle. In the upcoming slides, I will describe the design of Viper, and I'll call attention to the issues arising in machine code partial evaluation and how Viper deals with those issues. Before I proceed further, here's a short tutorial on IA32, which is the 32-bit subset of Intel's x86 instruction set. The ESP register is the stack pointer. The push instruction pushes an operand on the stack and updates the stack pointer suitably. For instructions with more than one operand, the operand on the left is the destination. So this move instruction moves bits from EAX to the EBX register. Square brackets denote memory dereference. So this move instruction writes the value 40 in the memory location pointed to by ESP. Unless you're dealing with an LEA instruction, which stands for load effective address. So this LEA instruction just increments the value of ESP by 4. That's all the IA32 you need to know for this talk. I'll use a running example to illustrate Viper's algorithm. This binary computes x plus y times n. The source code that produced the binary is given on the right. This binary takes three inputs, x, y, and n, which are available in the registers EAX, EBX, and ECX respectively at the beginning of the program. The binary computes x plus y times n in a loop, and the result is available in the EAX register at the end of the program. Now let's partially evaluate this binary with respect to the static inputs, y is equal to 1 and n is equal to 2. So the first step is BTA, and as we saw, one of the ways to perform BTA is forward slicing. For those of you who are unfamiliar with forward slicing, it is a primitive that computes parts of the program that might be affected by a given program point called the slicing criterion. There are existing tools that can perform forward slicing on machine code, so let's use one such tool to compute the forward slice for us. So EAX has the dynamic input x, so the first instruction is our slicing criterion, and the forward slice looks like this. It includes the entire binary. That doesn't seem right. Let's zoom into the problem. So the problem arises at the very first instruction, which is push EAX. Machine code instructions are multi-assignments. They have several inputs and several outputs. For example, the push instruction has two independent updates, one to the stack pointer and one to a memory location. This aspect of the language introduces a granularity issue during slicing. That is, although we would like the slice to only include a subportion of an instruction semantics, it is forced to include the entire instruction. So in this case, the ESP update and its successor, which are completely irrelevant to our slicing criterion, get included in the slice. Now, this effect can cascade. Irrelevant instructions can cause even more irrelevant instructions to be added to the slice, and the resulting slice can be extremely imprecise. Viper counters this issue by decoupling instructions that update ESP along with another location. So for example, Viper splits this push EAX instruction into an equivalent instruction sequence that updates ESP and the memory location in two different instructions. Now, if we compute the forward slice, we get the desired result. So Viper first decouples the necessary instructions, and our running example after decoupling instructions looks like this. Now, the slicing criterion is this instruction, which reads from the AX register, and the forward slice looks like this. As we can see, we have obtained the desired result. Instructions in the forward slice are classified dynamic, and the remaining instructions are classified static. In source code partial evaluation, we lifted static expressions occurring within dynamic context. In machine code, the expressions become instructions. So the equivalent thing to do would be to lift static instructions that produce values that might be consumed by downstream dynamic instructions. So Viper lifts the data dependence predecessors of dynamic instructions. That way, when the specializer residuates code for the lifted instructions, all the static data necessary for these downstream dynamic instructions would have been set up by the residual code. So here's our example after lifting the necessary instructions. And as we can see, the lifted instructions set up data for the downstream dynamic instructions. That concludes the BTA phase of Viper, and now we are ready to look at the specializer. Recall that specializer uses three primitives: eval, reduce, and emit. Eval and emit are pretty straightforward. Eval is just evaluation, and emit is just emitting instructions. So let's focus on reduce. In source code partial evaluation, reduce was implemented just by simple syntactic substitution. However, this approach doesn't really work for machine code because not all operands of an instruction are explicitly present in an instruction syntax, and some are baked into the semantics. For example, consider the push instruction. Just by looking at the syntax, it seems as if this instruction takes only one operand, the EAX register. But if we look at the semantics, we see that ESP is baked into the semantics. So if we use syntactic substitution, we won't be able to specialize an instruction with respect to its hidden operands. Viper counters this issue by specializing an explicit representation of the semantics of an instruction instead of its syntax. So Viper converts an instruction into a semantic representation that exposes all the operands. It then specializes that representation with respect to a store, and then it obtains a sequence of instructions that's equivalent to the specialized semantic representation. Viper uses quantifier-free bit vector logic plus array formulas to represent the semantics of instructions. It uses plain old symbolic execution to convert an instruction into a formula. And it uses a machine code synthesizer to synthesize an instruction sequence that's equivalent to a specialized formula. The synthesized instruction sequence constitutes the residual code of reduce. Now let me show you an example of reduce in action. So we have the push instruction. We convert it into a formula. As you can see, the formula clearly describes what the push instruction does. We specialize the formula with respect to the partial store, obtain the specialized formula, and then synthesize an instruction sequence that's equivalent to the specialized formula. All right, now that we have eval, reduce, and emit, we can build a naive specializer that works on machine code. So here's our example. Let me zoom into just the relevant portion of the binary for this walkthrough. And here's the initial store. The static input y is mapped to the value 1 in the register EBX, and input n is mapped to the value 2 in the register ECX. Now the specializer needs to be able to read and write values on the stack during specialization. So I've initialized ESP to a concrete address, say 1000. Now the first instruction is lifted, so we invoke reduce. So we convert it into a formula, specialize it with respect to the store, and then synthesize the residual code. We also evaluate lifted instructions because lifted instructions are originally static. The next instruction is dynamic, so we just emit it. The next couple of instructions are static, so we evaluate them. And we proceed in a similar manner to obtain our residual binary. Now, there's an issue with this residual binary. Even though it is the correct residual binary for our running example specialized with respect to our input store, our naive specializer treats specialization-time addresses and non-address quantities uniformly. As a result, specialization-time addresses get residuated as constants. In other words, the specialization-time stack layout is hardwired into the binary, and if we attempt to execute this binary under a different stack layout, then the binary might crash. One simple way to fix this issue is to classify ESP as dynamic at the beginning of the program. So we are saying the stack layout is going to be dynamic, it's not static. However, that would make the entire binary dynamic because all downstream instructions either directly or transitively use ESP. So we have a problem. If we treat the stack pointer as static and concrete, we get these residual addresses and we can't execute the binary. But if we treat it dynamic, then the entire binary becomes dynamic. So what do? Viper deals with this issue by treating the stack pointer static but symbolic. That is, stack addresses are represented by symbolic terms during specialization, and eval performs symbolic evaluation instead of concrete evaluation. That way, Viper will be able to read and write static values in the store during specialization, but it won't emit concrete stack addresses in the residual binary. And this approach doesn't apply only to the stack, and it's applicable to heap allocated storage as well. Now let me illustrate this symbolic approach to specialization on our running example. So here's our initial store. Again, the input y is mapped to the value 1 and input n is mapped to the value 2. However, we use the fresh symbolic constant boldface n to denote the base of the specialization time stack. This means that we are not constraining ESP to a specific concrete value. And before Viper residuates any code, it sets up the runtime environment of the residual binary by saving the base of the runtime stack in a dedicated location. Now in this example, I've just used the register ESI because it's not used elsewhere in the original binary. We will be using ESI whenever downstream residual instructions require the base of the runtime stack. We'll see an example of that shortly. So the first instruction is lifted. So we invoke reduce, we convert it into a formula, specialize it with respect to the store. Now the specialized formula contains the symbolic constant n, which denotes the base of the specialization time stack. But the residual code must contain the runtime counterpart of n. So we substitute ESI, which denotes the base of the runtime stack, for n, which denotes the base of the specialization time stack, and then we synthesize the residual code. We of course symbolically evaluate the lifted instruction because it is originally static. The next instruction is dynamic, so we just emit it. The next couple of instructions are static, so we symbolically evaluate them. And the final residual binary looks like this. As we can see, this binary does not contain specialization time addresses residuated as constants. However, static non-address quantities are still residuated as constants, and that's the desired behavior. So that concludes the specialization section, and more information on topics such as safety criteria, theorems, and threats to the validity of our approach can be found in our paper. So let's move on to experiments. Viper was designed for two principal use cases. One is to specialize binaries with respect to common inputs, and then to extract an executable component by specializing with respect to a flag that selects that component. We used different test suites for evaluating the two use cases. Here are our results for the first use case. Our test suite consists of 7 IA32 binaries. The first 5 came from micro-benchmark programs written by us, and the last 2 came from open source FreeBSD utilities. The sources of the binaries ranged from 19 lines to 167 lines of C code. For each binary, we classified some of its input as static, and we specialized it with using Viper, and we compared the execution time of the original and the specialized binary. So the lower the specialized bar is with respect to the original bar, the better. So for PAR, you can see that Viper produces a slight slowdown. PAR has a tight loop, and we believe that the aggressive loop unrolling done by Viper disrupts instruction caching, leading to a slowdown. At the other end of the spectrum, we observed a speedup of 1.9 for filter, which applies a static convolution filter on an image matrix. The average speedup we were able to produce for our test suite, computed as a geometric mean, is 1.3. Here are the results for the next use case. We extracted a single component from each of the 3 binaries obtained from open source programs. We compared the size and the number of procedures in the original binary and in the extracted component. For B64, the component is slightly bigger than the original binary because our specializer does not optimize the layout of basic blocks to reduce the number of jump instructions, and the component contains many more jump instructions than the original binary, resulting in a larger size. So in conclusion, I presented an algorithm for machine code partial evaluation. I presented Viper, which is a partial evaluator for IA32. We looked at the issues arising specifically in machine code partial evaluation and how Viper has novel aspects in its design to deal with those issues. Thank you.
Hi.